Good, then. Good morning online and here. Welcome and thanks for attending the next workshop or course in the CBBS graduate course program. Let's call it that. So these workshops exist because I want them to exist, because I think in general, the education of people working in research can be improved, and that's why these workshops exist. And I'm happy that that some people are actually interested in also attending these workshops. Now, somebody else online. I see some new faces, I think. Who has attended a workshop before? I think you're new, but you have attended one before. You no, it's my first one. It's okay, good. So online, I can't really tell. So maybe then before we start with the content, a little bit about myself so that you know who I am and what's going on and what it's all about. So I'm Dirk Ostwald, as you might have figured. I'm professor at the OVGU at the Institute for Psychology. This is not showing up. Sorry. The chat wants to tell me. Oh, okay. Somebody online wanted to tell me that's their first course as well. So maybe people online, can you, if you want to interact, can you just speak? Because if it's in the chat, it always changes the layout of my screen, and that's a little bit irritating. So just unmute yourself and just say something. Thank you, like we do here in the room. I'm Dirk Ostwald. I'm a professor at the Institute for Psychology, and they're professor for data analysis, essentially. I have a background in neuroscience, mathematics, medicine, psychology, whatever, and spent the first part of my academic career in Berlin, so a big part, let's say. I've joined OVGU in 2021, so last year. And so the research we are doing is computational cognitive neuroscience, so a lot of decision neuroscience work, essentially, and methods in cognitive neuroscience, and teaching-wise, I'm representing data science. We are in the process and have now already did one first iteration of this whole curriculum, because I've spent one academic year here. Of a data science curriculum for experimental psychology and neuroscience. This is not the Eid book, statistics, German Psychologie Statistik. We don't know what we are doing, but we do t-tests and p-values or something like that type of statistic. It's different, so it aims to go to the foundations, and the foundations are of course mathematical, and establish them properly so that we can properly build on them and discuss probability theory and statistics and probabilistic modeling and Bayesian statistics like the whole world does, and not like German psychology professors often do or have done for the last, 30 years. I don't know when it went wrong, but it went wrong at one point. So we are basically going a little bit back to basics. All of this you find online and can look up, and of course you can also join all our courses. Most of the stuff is happening in the bachelor and the master for psychology, so mathematical foundations, probability theory, frequentist statistics. That's core curriculum in the bachelor, as well as the GLM, that's a bachelor. Bayesian statistics, I'm looking for outlets and maybe we put some in the bachelor, maybe not. There's a lot of other stuff to learn as well. And we're obviously doing it here. Multivariate methods, that's master program. So that's the master in psychology. And programming we do in other courses in psychology and also in these graduate courses. There's more to come. So you can find out all about this on our homepage, where you find what's going on. We will at one point also have the English version of that when time allows, and or somebody is so kind to translate that. But of course, we also need the German website, because for some reason the official language seems to be German at a German university, which of course could be changed, but apparently too many people don't want to change it. You can look up everything that we taught so far, or let's say since 2016, 17 on YouTube. So there are many playlists referring to all the courses. So if you want to learn more, that's where you can look. And maybe before we go over these things, I mentioned that for this course we are doing here, we also have a course website, which is located under the CVBS imaging platform, because these courses are also part of our CVBS imaging platform initiative. And that's where you find the materials, and where you also will find the videos, because we are recording this stuff here. So you should be aware of that. And if you don't want your privacy to be my English, I'm teaching all the time in German. If you don't want your privacy tainted, whatever, then just don't violate it. That sounds a little bit hard. Then just don't talk or walk into the camera. Otherwise, we can, of course, also, if you later on want to remove things, we can also remove that from the videos. But you should be aware that this is going to be recorded and is going to be available in a non-safe space online, namely YouTube. Whether that's the best outlet, I don't know, but it's very practical. Good. So then that's kind of the bigger picture of where we are coming from. So hit the bell, or whatever these people always say when they do YouTube videos. So if you want to get updated and so on, click notifications and hit the bell or whatever. So you can, if you want to learn more, look there. A lot of stuff in German, unfortunately, but maybe in the long term, we switch also in the bachelor to English, if the world allows me to do that. But that's a long story. Good. So that's where I'm coming from. So we are actually located at the OFCO main campus, so not here, but then we do home office most of the time anyway. So bigger picture of where I'm coming from and what we are doing is here my little science sketch. So that's basically how we view science. So there's something that we call reality. We can record data from reality. That's actually how this thing happens, going from reality to data. That's the big topic of measure theory, mass theory, not mass theory, but mass theory, measure theory. I think it's right. So we will actually investigate that in the winter term. That's something novel. I used to ignore that because it's also a little bit boring, but then also interesting somehow. So what we've mainly been doing, and what all of my courses are about, is what you see here on the right side. So data analysis from a model-based perspective. So there is no model-free data analysis, whatever people want to tell you. You always formulate a model, and it's good that you know what this model is about, and it's a big part of science, formulating models. And then you estimate that model, so you inform the model by the data, and then you evaluate that model, and you think about whether it was good, useful, or whatever, interesting, and then you go back to model formulation. So that's the kind of very big picture philosophy behind what we are doing in terms of methods education. As I already said, we consider all of this data science. So what do we mean by data science, specifically here in the setting of the CBBS? There we, of course, have or maybe CBBS and, or let's say our group and parts of CBBS, because of course CBBS is more than cognitive neuroscience. So we definitely in data science, you always have this one application field that you're interested in. I think for your community, that's neuroscience. For myself, that's cognitive neuroscience. But of course, in the 21st century, and trying to kind of keeping up the quantitative scientific philosophy that was established over the last, I don't know, 300, 400 years. This is, of course, merged with things like computer science and programming. So if you want to analyze data, you will not do that and using your pencil and your mental arithmetic, but you will use a computer. So you should know how to use a computer and how to automate your analysis, and how to also document them and make them reproducible in terms of programming. So that's, of course, then part of data science. And then there's, of course, the theoretical part, which is, of course, what you would call mathematics and statistics. All of these things have overlaps, and maybe call it machine learning, digitalization, or quantitative research. But that's what we see as data science, and that's what we do, and that's what we believe in, and that's something that is good if you like to be rational. So it's all about rational. If you don't like to be rational, then screw all of this and just do whatever you want and whatever. So this data science, I don't know who of you is aware that there is something like data science. Yeah, most of you are aware. So data science exists. There are actually also study programs at OFGU in data science, and we started to call everything that we do data science, because I don't like most of the other terms. So statistics always has this German psychology, statistic. We don't know what we're doing, although mathematical statistics is a proper, very interesting, good field. Machine learning is the computer scientists not knowing what they're doing, so that's also annoying. That's why I don't call it machine learning or artificial intelligence. And data science, I think, is the although there you also have to watch out that people don't mean just getting data organized into databases, and that's then data science, but to create meaning from data, and that's what data science is all about. And I'm talking more about that in the undergraduate courses in psychology. There are, and this is just what I want to highlight in terms of data science, this exists and is essentially science in the 21st century. And the people online, if you don't want to say something, mute yourself, because sometimes we then have these noises, and I'm very sensitive. Sorry. There exists journals, and this Harvard Data Science Review, if you want to get an impression of what data science is and how it relates to your research, have a look there. It's very all-encompassing and broad and good, but also up to date and deep and so on. It's not just sometimes if you Google data science or something like that, you end up in these kind of settings where companies want to sell things. Now my mouse is blocking. That's Always. I'm pushing my machine here a bit hard. I try to uninstall software. I want to let her in, but my mouse is not working. Let's do like this. Oops. So. So have a look there if you want to learn more about data science and how it relates to your research. Now, getting a little bit closer to what we want to do in this workshop. You kind of saw that the name is Foundations of Bayesian Inference. So I assume that you have heard the term Bayesian Inference or Bayesian Statistics before. Who took a course in Bayesian Inference before? No one. That's of course fine, because most of the teaching that is done is frequentist inference, which is what it is. And you always think, well, when I was young, I thought in 5 years everyone will be a Bayesian, and it never happened. And it's unlikely that it will ever happen, but it exists. So I view the whole thing of probabilistic modeling or probabilistic inference as kind of a big topic. So you use probability theory to learn about the world and quantify your uncertainty, or not to learn about the world, but you use models to learn about the world, but to quantify your uncertainty about these models, you use probability theory and probabilistic inference. And there are, that's just how it is, there are two big schools in probabilistic inference. One is frequentist inference and one is Bayesian inference. And frequentist inference is that what is mainly taught in undergraduate statistics courses, especially also, of course, in psychology, but not only there. You can say you don't like that. I don't actually have a frequentist inference is fine, Bayesian inference is fine. There's nothing wrong with fundamentally. Well, there's something fundamentally wrong with frequentist inference, but then there's also no point in not teaching that. If the whole world wants to do p-values, then we do p-values, whatever. But so I see both of them as part of a bigger whole. So there's probabilistic inference. They also are not that different, and they have their conjunctions, intersections. So yeah. If you go deep into either one of them, then you see the parallels, and it's not that big of a chasm between this way of thinking and that way of thinking. Before we actually start with things and so on, let's briefly review what the central postulates of these approaches are, so that you are aware of where we are going here. So the main difference between frequentist inference and Bayesian inference relate to interpretations of probabilities and to statements that one wants to make about the world. They don't relate to anything like probability theory. So do a course in probability theory. It will help you a lot in frequentist statistics. It will help you a lot in Bayesian statistics. It's not that there's a different kind of form of probability theory for either of the approaches. It's the same probability theory, of course, but how probabilities are interpreted. So, and by probabilities, I, of course, may always mean the mathematical entity of a probability, not something in the world, but the mathematical model. How these are interpreted, that's different in frequentist and Bayesian inference. So in frequentist inference, probabilities are typically interpreted as limiting relative frequencies. So in a way that probabilities really exist, but then as limiting relative frequencies. So if you throw a coin and count the number of heads and tails, and then average over them, you get to 0.5. And then if you would do that until infinity, that then would be a probability. So also these probabilities don't really exist because we all will die and everything is doomed. And in the end, there will be no world anymore. And that means this idea of a infinite sequence is also just an ideal. So also there in frequentist inference probabilities don't really exist, but nevertheless, there's some belief that something like probabilities actually exists. And yeah, that's so if you go to the core frequentist belief. Parameters in frequentist statistical models are considered fixed unknown constants. So you all, who has heard or who has done a t-test? Good. So you all have done a t-test, and there you had, I hope you didn't call them population parameters, but if you call them population parameters, so be it. So there you had parameters, and you estimated these parameters using means and standard deviations or sample standard deviations, sample variances, and you estimated them using point estimates, and then you formed the ratio, and that was your t-value. And these population parameters that you, or maybe even the population t-value, which is never discussed, that you estimated, this was considered to be fixed and unknown. Even after doing the t-test, you didn't know the population parameter, but you had estimates for it. And you estimated it by point estimates, and that was essentially it. So you didn't make any probabilistic statements about the parameters. So, and if you then try to say what a good frequentist procedure is, you look at the long run frequency properties, so things like bias and efficiency, sufficiency, and you look at what happens if you sample data repeatedly, how then your statistical procedure performs. So that's what you do in frequentist inference. And of course, you're all aware of that because that's what you have been using and learned about and use, I guess. Bayesian inference starts with a different perspective on probabilities. So essentially, with the idea that probabilities represent degrees of belief. And basically leaning into what is a little bit more common language about probabilities. So you, of course, say the probability that it will rain this afternoon is 0.5 or whatever. And this is, of course, not a limiting frequency because this event that it will rain this afternoon, you can't really say something about a limiting frequency because you can't repeat it. It's this afternoon. It's only this afternoon. It's the same with elections. The probability that, I don't know, or the probability that Putin will win the war or Putin will lose the war. These things don't have limiting frequencies because this will be his only big war. I think we can predict that much. Well, maybe we can't. Sorry, the example is not really great. It's better with elections because elections happen, they have a fixed date. That's when the election happens. And then the election is over and there's only this one election. And this definitely doesn't have a limiting frequency. Whether Putin will start more wars or not, we don't know. And we hope that he will not. So the interpretation of probability is in terms of degrees of belief and uncertainty. So you don't think you sample something. That's the most important thing. You don't sample anything. It's just describing your or our, not only your, but the human uncertainty about things. And that's, people have sometimes a hard time getting their head around that. It's just that in the end, everything in probability theory and Bayesian inference is uncertainty quantification. We just don't know what the future will bring. We are uncertain. Everything is uncertain. And it's, of course, not easy to live with uncertainty, but everything is uncertain. We don't know whether this building is going to collapse today or not. We hope that it won't, but we are uncertain. But we are fairly certain that it won't. The only thing that Bayesian statistics does and how probabilities are viewed is as a quantification of this uncertainty. And that's something fair. The question is, why do you need that? Why do you want to quantify uncertainty? Well, you could also say, well, you don't need to really quantify it. You just need a feeling that it's okay-ish, but I don't need a number for that. And then it's, again, if you want to make rational decisions and you have multiple options to make a decision, and you want to make it rational as good as you can, then, of course, it makes sense to quantify things. But still then, even if you have quantified everything, you have to make a decision. And then you might not follow what seems to be in light of everything that you know what seems to be rational, because you just don't want to be rational, which is, of course, fine. The parameters in Bayesian models are unknown and fixed constants, like in frequentist statistics, but you make explicit probabilistic statements about them. So you say something, the probability that the true but unknown value for my expectation parameter for this t-test is larger than 0 is, I don't know, 0.7. So you make probabilistic statements about parameters, and we of course we will look at that. With these probabilistic statements about parameters, which you just don't have in frequentist inference, at least not in this sense, so you don't have a probability distribution over parameters. Of course, you have confidence intervals, and there you have a certain probabilistic statements about parameters as well. We don't talk about this here, but so don't get confused there. But even there, you don't have a probability distribution over parameters. You have them here, but you always have to be very clear about, and we will look at examples, of course, but you will always have to be very clear that this is not a probability statement in terms of parameters in the world. It's not that you think my prior distribution is so it's out there, but it's a quantification of your uncertainty. If you then go deeper and you enter an empirical base, then of course this can again get blurry, but that's not what we are at all yet. So the probabilistic statements that you make about parameters are always the human description of uncertainty. They are not things that describe the external world. Good. So that's kind of the big highlights here. Are the questions about this distinction between frequentist and Bayesian, where you're already confused? We'll of course have a close look at Bayesian inference here, because the course is called Foundations of Bayesian Inference, and the probability distributions that we will look at, and we will of course always again also clarify how to interpret them. But you also have to in your head distinguish a little bit between the mechanical framework that allows you to do inference. So you define a model, and then you have some procedure to create inferences and statements, and the interpretation of that, because they are not the same thing. So one thing is happening in the mathematical or applied mathematical world. The other thing is what this now means for the real world that you believe to be in, and what you should do with it. So we will, and then of course multiple interpretations are sometimes possible. So the plan for the course is, after this introduction, which we are doing now, and to go to the foundations of Bayesian inference, and then discuss conjugate, numerical, and variational inference. And on the next slide, I've highlighted what these things will cover. So if you ever Google Bayesian statistics, you will always find this picture. It's horrible, confusing. So I really hate this picture. I just brought it up because it's because you always see it, and people think that this is something, or this is Bayesian inference. It's very confusing, especially with the likelihood being plotted at, on the same outcome space as the posterior and the prior, because these two are probability densities over parameters, and this is a density over data. So the x-axis is different for this blue, and so it's the same for this, but it's different for this. And sorry, people online can't see that, but I also can't use my mouse. So it's a horrible picture, very confusing. One can get some sense into it, but that takes some time. But anyway, you always see this picture. You always, of course, see the Bayes, Thomas Bayes portrait, and you, of course, always see Bayes' theorem, which is also very confusing if you look at that, because it talks about events here, so probabilities of A given B, and there you see densities, which is, well, you can maybe try to interpret A given B as random variables, but nobody writes random variables as A and B. Anyway, you always see this picture, although it's quite horribly wrong. And we have to talk about the foundations, and this is what we will cover there, namely prior likelihood, posterior, marginal likelihood, and then things like maximum a posteriori. That's the first typo I see here. MAP estimates, so maximum a posteriori estimates, and credible intervals. This is what we will cover in foundations. Then we're going to discuss conjugate inference. I didn't find picture that nicely represented that if it wasn't the proper models already. So I used a cartoon. It's quite lame, but it's there. In conjugate inference, this is what, if you heard machine learning talks, what people then also call closed form solutions. Conjugate inference is basically very, in spirit, it's very similar to undergraduate frequentist statistics. So you have fairly simple models where you can derive things that you want to derive in Bayesian inference, like the posterior distribution analytically, meaning by writing down the math, and then you're done, and you have solutions which are then quite simple. So you have to add a couple of things, and then you have the posterior distributions, things like that. And they are nevertheless, so didactically, of course, important, because that's where one can start out. The better binomial and the Gaussian models is what we're going to look at. They are also applicable in research, so there's nothing wrong with them. So we've been using the better Bernoulli model for EEG data analysis over the last 10 years. So it's the most basic Bayesian model that has been around for 300 years, but we can use it, so with some modifications, but we can use it. So there's nothing wrong about these models. It's not what you will find if you go to a, I don't know, machine learning conference or something. Is something that is very exciting and hip and something like that. That's very basic. Yeah, we will have a look at that. Who has anyone studied better Bernoulli or better binomial models? No, so that's then also new. That would be so our first exploration. Then we're going to discuss numerical inference, which is basically an approach to do Bayesian inference with models that are different from the models that are conjugate. That's then always with the idea that you have kind of a general procedure to do Bayesian statistics with any model that you like. So that's kind of the general spirit there. Same goes for variational inference. For some people, numerical inference and Bayesian inference is Bayesian inference, I sometimes feel. So that's also a psychology feature, I sometimes think. The point here is that you use numerical integration or stochastic integration to solve integrals that you need to consider in Bayesian statistics. And you have kind of general purpose methods to do that. I have to say I didn't grow up in numerical inference. I grew up in variational inference. And I always and still look at numerical inference as a kind of a potpourri of methods with not a clear. So there are many things that you can do, and we will look at them, and you can do them, but it's not a very coherent body of work with a all-encompassing theory, although I think one could build it. One thing that I also didn't like is, and still don't like about numerical inference, that you have to turn on random number generators to do Bayesian inference, and that it's in this sense not reproducible. Because of course there's randomness in your data analysis, which is not a nice feature, but I don't want to bash or slack off or whatever numerical inference too much. It's not where I grew up in. I'm looking more into it. And there's also some fusion going on with where I grew up in, namely variational inference. Variational inference is also a form of approximate Bayesian inference. It's also the idea that you do inference for any kind of model, not only these simple models that have been around for a long time. It doesn't, in terms of numerics, doesn't rely on stochastic simulations, so random number generators, but in terms of numeric relies on optimization. So trying to find maxima of functions numerically, like basically everything that you do in model estimation. It has a nice theory or a coherent theory, it's also, it has this kind of this general purpose tool. It's also, if you are in cognitive neuroscience, you might have heard it under the label free energy principle, maybe even. Has anyone heard about free energy principle? That's no, free energy principle, that's Carl Fristen's work. And the idea of the free energy principle or active inference is that the brain does variational inference. That's what the free energy principle is all about. In cognitive neuroscience, and I think in brain science, and I think in general science, it's actually it's a proper idea. So there are a few proper ideas in cognitive neuroscience I find, except now the idea is the brain is a neural network. Well, we've been that far before. So the free energy principle is a proper idea. It's basically the idea that, of course, the brain is doing what our most sophisticated machines do, namely learning from data and doing statistical inference. But that's all variational inference. And because in the end, I'm a brain scientist and I'm interested in what the brain is doing. And I figured that a contemporary idea about what the brain is doing is free energy principle. I got into variational inference, but variational inference is not only the free energy principle. It's basically the free energy principle. It's just an application of variational inference. Variational inference is the bigger topic. Today it's called, so if you are into machine learning, people call, and we'll have a look at that also in the history a bit, it's now called variational autoencoding. That's how people call variational inference. Now I also changed, I used to call it variational Bayes, now I call it variational inference. It makes sense. It's a broad thing. So that's will then be the last bit. So what time do we have? Yeah, maybe before we go into that, that's my timetable suggestion. So I kind of like these 45 minutes on and 15 minutes off things, because I figure it's demanding. The idea is to do 5 hours today, tomorrow, and on Friday. And my suggestion would be that we follow this timetable. So that we would be done by 2:45, basically, so at 3. Are there things against that? Is the lunch break too short? So good. Okay, then let's do it. So with the lunch break, one can do 2-hour lunch break, but then it's dragging on quite late into the afternoon. So that's why I thought that would be the idea. Okay, yeah, I think this also then would be a good time for first break. So after the break, I want to review a little bit the history of Bayesian inference, so that you are aware that this is not something I invented yesterday or something, but this has a long history. And then check a little bit on your mathematical preliminaries, so that we have some things established before we go into Bayesian statistics. Are there questions right now that you want to clarify? What's from the people online? Okay, for the people online, I will close the room in the breaks, because only then the video is actually saved. I don't know what Zoom is doing. I think it uses then the my machine to render the video, so to write all of the frames into one file. So that's why in the breaks the room will always close, and then I will let you back in. Good, then let's have a first break, and then delve into the history of Bayesian statistics and the things that we need to know about it. Then let's continue. And before we actually going to discuss the content of Bayesian inference, I wanted to highlight some aspects of the history of Bayesian inference, because I think it's important to realize that Bayesian inference or Bayesian statistics or probabilistic inference or something is nothing novel or the new thing or something like that, or the next big thing or something like that. It's something very reasonable, so it makes a lot of sense to quantify uncertainty if you want to be rational, so that it makes sense, but it's not something that just was invented by some machine learning people in the 2000s or something like that. It has been around for a long time, as long as probability theory has been around. And so I'm highlighting some aspects in the history here. This is from an article by Feinberg, which I also could have cited, of course. It's not purely from that article, but that's a very good article on when Bayesian inference became Bayes, because it wasn't always called that. When preparing these slides, I realized it's a very non-diverse history. So this will all be white European men who come up here until today. So this history will gonna go on until 2017. It's not European, then there will also be Americans, but it's very non-diverse. So I apologize for that, but that's from this paper, essentially. That means more research is necessary to figure out other contributions to Bayesian inference, not only by white European or Anglo-American men. So sorry for that. So the story starts somewhat with Thomas Bayes in 1763, which was actually not when this paper was written, but when it was presented. So we will have a look at Bayes' theorem later on in this publication, or in this research work by Thomas Bayes. Bayes' theorem doesn't actually show up. So what this was about was the better binomial model with a uniform prior, and we will discuss better binomial models. So this is where this somehow started. Laplace then also in the 18th century worked on essentially the same thing. And then, a couple of 50 years later, of course, there are many more publications, or it's a little bit unclear, but these are not the only things that happened, obviously, in these almost 100 years, but things that one can still identify based on the records and so on. And the research that people did into these origins. By 1837, what Laplace did and what Bayes also did was then labeled as inverse probability. The whole thing wasn't called Bayesian Inference at that time. That only came later. This was actually more, so Bayesian Inference later was invented as something by the frequentists to say this thing of doing inverse probability is bad. So they called that Bayesian as a derogation. Is that a word? So when you want to have a term that implies that something is not cool. This kind of probabilistic inference that we're going to discuss in these days called Bayesian inference, that was known as inverse probability, basically throughout the 18th and 19th century. Another early work, there is essentially by Bienheim on the Dirichlet multinomial model. So these are, if you open modern machine learning textbooks that have a probabilistic flavor, so the good ones, not the ones that are called deep learning or something like that, but the good ones that appreciate that the whole thing didn't start in 2012, but a little bit earlier. They will cover, of course, the better binomial model and the Dirichlet multinomial model, but this is old stuff. So this is 250 years old. And before that, if you dig deeper, you will, I guess, also find things that where these things came already played a role. But kind of this modern history of the origins of Bayesian inference is basically looking at these things, and we will discuss the better binomial model. But then we also know that this is was not invented yesterday. And this whole thing was called inverse probability. Then that was kind of 150 years. Then one period that is quite important, of course, for modern data science, statistics, probability, theory, inference, whatever, is the first half of the 20th century. Where the first thing that happened, and that is still, of course, felt today, is that some people, including Fisher, but also, of course, other people, so I also don't include, obviously, everyone here on the slide, so I just picked Fisher as a kind of frequentist a poster boy. They wanted to do something better than inverse probability, and so something better than Bayesian inference, and started the whole frequentist approach. One has to say that also this idea that I presented in the very beginning, so this idea of what probability means, whether it's something that describes your uncertainty, like Bayesian inference, or something that is part of the world, that was not that clearly communicated until, let's say, 1950. So although people worked with mathematical probabilities and obviously did reasonable stuff, they not necessarily always communicated clearly what these probabilities actually mean. Is it their uncertainty? Is it something that they think exists in the world? this started to form a little bit in the first part of the first half of the 20th century, and then, of course, under frequentists, under the frequentist guard. Of course, also with this idea that we'll come to that. Of course, something that a naive criticism of Bayes is always is that you have a prior, and then you say you don't want a prior, you want to be objective. And this was, of course, something that also the frequentists discussed. Fisher invented something weird that I don't really, I think nobody ever understood, but that's this kind of fiducial argument. Has anyone heard about that? That's something that goes into the Bayesian inference direction, but not really. But I think nobody really knows what Fisher wanted to do with that. But of course, other things that Fisher did, like maximum likelihood estimation and ANOVA and p-values, not hypothesis testing proper, but p-values, that's still around today. And yeah, I don't know. It's funny to read the history about Fisher. He was sometimes quite aggressive in what he tried to convey. So while this all started, and of course dominates textbooks, so of course the other people that play a role there are Pearson, both the father and the son, and Nyman, so hypothesis testing. I guess you all know the story that the Fisherian testing and the Nyman-Pearson testing are very different, and they are very different. But still, this is kind of was then merged in the 50s, and then now you have what you find in these kind of weird psychology textbooks or social science statistic textbooks that don't discuss the math, but the statistics. And you have this kind of weird thing that everybody hates, and everybody thinks statistics is horrible, and rightly so, but that's kind of originated there. But then, of course, was, if you look into the real publications by these people, also Gaussian, of course, the student or T distribution, that's proper. So they knew what they were doing, and they had their reasons, but somehow then, it get to this dominating thing, and it's still what everybody is doing for whatever reasons. Anyway, at the roughly, or not exactly the same time, but briefly afterwards, and actually other people like Definetti and Jeffries, they also, in kind of counteraction against frequentism, or just basically in thinking about what they are saying and thinking, it can't be quite like that, they established this notion as probability as uncertainty quantification and communicated that quite clearly. So for Definetti, I always remember this: probability doesn't exist. That's how he starts his system for probability. So you have to also keep in mind that also Kolmogorov at the roughly the same time laid down his axiomatic system for probability theory, which is still the main thing that in use, so that you go to the foundations, you say we define this, this, and this, and then the rest of probability theory follows. This is what also other people did. Harold Jeffries as another one. You might have heard about Jeffries priors, if you heard something about priors. So this was happening at that time, but there was not so much with applications in mind, but this was more about what does probability mean? What do probabilistic statements mean? And it's all good stuff. There's nothing wrong with that. It's fairly, whenever you go to the foundations, it's things that you then say, yeah, that works well in textbooks, but in real life, I have much more complicated or complex problems. So that's why then, of course, this is also goes into kind of a philosophical area of science or math or whatever. But yeah, so that's when this thinking about subjective probability started to play a role. And what also then, of course, World War II happened, and World War II brought then kind of some activity that's also very interesting in the statistics communities, or kind of helped establishing statistics or data analytical communities, because there were actual problems like figuring out how to essentially better kill other people, but which is of course a bad thing. But nevertheless, there are many things that origin from that time. So Turing also did work in Bayesian inference, and of course also invented the computer. I think it's not that easy, but so the war effort, like it's always described, led to quite some movement. Also, Abraham Wald and the sequential likelihood ratio test, which maybe people in psychology these days think about it in terms of drift diffusion models, or sometimes they make these links to likelihood ratio tests. This happens, a lot of stuff happened in the war. One thing that, because there were actually military problems, dual use and so on. And one thing that was fairly important for Bayes and inference then later on was the invention of the Monte Carlo method, so numerical inference, which was not conceived at all. If you look at the Metropolis Uma, the second author paper, that didn't have to do anything with Bayesian inference in the early days. That only came later, but that happened kind of in this period. So on the one hand, in the early 20th century, you have this establishment of frequentism, which we still teach today, and I will start teaching again next week in psychology undergrad statistics, and people do their GLMs and so on. But you also have this thinking more about probability and what does it all mean from the uncertainty quantification. When I mean subjective, when I write subjective probability, that means uncertainty quantification. I think that's a better term for it, but it's often framed like that. Then actually, so the big, the big fight, if you want, or the more established, the biggest establishment, the bigger origins, or the stronger origins in Bayesian inference as we see it today, were then basically happening after the war. So one key person there is Savage in his book Foundations of Statistics. If you read the history, then it's always that these people all knew each other, and they were. This was at that point, of course, still a fairly small community. They all knew each other, worked at different universities in the UK and the US, and so in terms of Savage, the idea that you quantify uncertainty and you make decisions based on that, using the framework of what is now called Bayesian inference, that happened fairly straightforward, or fairly early on after the war. Of course, also based on things that they did in the war in the research projects. It's also, if you look into the Savage book, it's also that it's not calling things Bayesian inference. So it's always a little bit of a disappointment if you want to go to, so you think you want to learn about Bayesian inference, and then you hear, okay, that was started by Savage in 1954, and then you open the book, there's no Bayesian, it doesn't use the word Bayes at all. So maybe Bayes theorem shows up, but it doesn't say Bayesian inference. That only started in that period. I mean, Fisher called something Bayesian inference, I don't know, in 1930 or something like that. And then people started to use the term. It's a little bit like deep learning. I mean, you all have heard about, when you were younger, that there are things like neural networks, and they were called neural networks. At one point, things started to be called deep learning. And you don't know why that happens, and it's just confusing, but it has to do, of course, with also branding. This is a lot of things. So, of course, people always want to, in academia, want to do something novel, and then it's one way to do that is to give a new name to something that has been around for a long time. Alter Wein, neuen Schläuchen, I think is a German saying. A very good book that I highly recommend is then the book by Pratt, Reifer, and Schleifer from the 60s. I think there's an earlier version. This is the Introduction to Statistical Decision Theory, which actually was not properly published until 1995. That is really a very nice and grand and encompassing introduction to Bayesian inference and its use. So in science, that's, of course, we want to quantify uncertainty, but in real life, we also want to make decisions based on our quantification of uncertainty, and that's what they really work out there nicely. Of course, this then goes also in the directions of operations research, Markov decision processes, and so on, but it's still not quite that. And it's just very good, very clear, and very aware of what they're writing about. So it's not just presenting some math and saying, here, that's the proof, but also describing what they actually want to do with that. Lindley then has been very active in pushing the Bayesian inference approach. He was also heading for some time statistics laboratory in London, I think. And I just picked here the base estimates for the linear model from 1972. There is one important thing that all these people discuss always is very important, but which I've never really studied, so I don't put it up here, is that I think also in the 50s, the likelihood principle was invented. That I still haven't grasped the deepness of the likelihood principle, I think, because if one states it is so that everything, essentially the data informs the model via the likelihood. So at one point I will talk more about the likelihood principle. That also happens around this time. And then, of course, also at this time, so around the 70s and so on, the Metropolis Hastings algorithm for numerical inference started. So basically going back to the papers by Metropolis. So there was activities in terms of numerical inference then in the 70s and then the 80s. So something that is fairly nice if you want kind of a fairly recent but deep dive into Bayesian inference. That's the book by Bernardo, Bayesian Theory. I think he was, if I remember correctly, he was a student of Lindley, so there's kind of a lineage there. And then, of course, computers rose more and more, and then computer scientists became interested in statistics and called this thing machine learning. And one thing that I highlight here is the work by Michael Jordan, who has this book on learning and graphical models, which the good thing is about, so in machine learning, you have a lot of people who have no idea about probability theory and basically do their neural network stuff and then interpret the result probabilistic or something like that. And but you have also people who are well aware that the world didn't start when Bill Gates invented the computer or something like that, which of course not what happened. So that this is a part of a bigger history of data analysis, and Michael Jordan is one of those. So that's good machine learning. And this learning graphical models, that was always what people then in the early 2000s, when I entered the game, not really, but I at least I was in Tübingen and I went to the machine learning summer school, and I always referred back to Michael Jordan. So here on the since 2000, where I see most of the, well, that's a very personal history in a way. Variational inference really only started in the 90s, and I think Suvan Gavarani and others, and so he had this thesis with what's his first name? Don't know, Beer, but Beer. There was this PhD thesis by Beer Geoffrey Hinton also made contributions to variational inference, and David McKay. So there was in the 90s, variational inference started a little bit. So that's also in terms of, I didn't put it here because I don't know the history that well about numerical inference. That started somewhere when the computers came more available and people realized that they could do numerical integration using computers and doing Bayesian inference somewhere in the 60s, 70s, 80s. But the thing that I'm very interested in, variation inference, then really started only in the 90s. If you go, of course, you can also find earlier things, but the 90s and then the early 2000s. The free energy principle, which for cognitive neuroscience is, of course, something that was first communicated in 2006. Free energy principle. So again, free energy principle is the idea that the brain does variational inference. That was basically what Carl Friston got out of discussions with Geoffrey Hinton, I believe, when Geoffrey Hinton was in London. And that's when I also entered kind of the field, and there was a lot of variational inference, and neural networks were not interesting. And then actually what happened was, as you might know, that deep learning came around. So neural networks were in again. I put Geoffrey Hinton down here. Of course, he has done many more things, but of course, he also pushed that at that point. And then variational inference was not, or I think it's still not as prominent as it should be, or so basically probabilistic modeling, Bayesian inference in a proper setting. But there's a lot of neural network stuff happening. For some time, I thought everybody has forgotten about variational inference. Because really if you look at, for example, machine learning summer schools and so on, in the 2000s, Bayesian inference was all over the place. So Bishop and everybody was talking about Bayesian inference, Bayesian inference, Bayesian inference. And then 10 years later, nobody was talking about Bayesian inference. It was all neural networks, neural networks, neural networks. Luckily, some people, luckily or not, people like Dieter Kingma then gave a new name to variational Bayes, which has something in there that also reminds people of neural networks. And so they call it variational autoencoders. It's variational inference, but at one point, at a very small point there's a neural network in there. So that's why variational inference still lives on, which is a good thing. And probabilistic models live on. You might have heard these diffusion models these days that generate images. That's something that's popping up this year, where you enter some text and then an image is popping up using a variational diffusion model, whatever that means. I mean, an image also pops up if you type into Google something, and also an image pops up. Anyway, and something that I really like to see from the machine learning community, David Bly has this paper from 2017 on variational inference for statisticians, which is quite interesting because this kind of modern approach to inference is actually happening a little bit removed from the statistics community, but then not really. And then these kind of papers, they then give crosstalks. So why all these white men here? Well, it has a history. So Bayesian inference is not something that is now coming around and tomorrow everybody will be Bayesian and yesterday it wasn't. But it has been around forever. It has been around longer than frequentist inference. Why frequentist inference dominates as it does, I can't tell you. I think I'm also guilty of having it dominate, because the course that I will give in the bachelor and the master, there will be frequentist inference. But then the problem is, if I don't teach them frequentist inference, my colleagues will say, "Oh, you didn't teach them frequentist inference." And then it's like, so maybe I'll get more. But then the other thing is, there's so much to learn, and one should have more courses. That would be the best. So that would be the frequentism course that we do in the winter term, so probability and frequentism, and then we do another course on Bayesian inference, and then you have the whole picture. And this is why we're doing this course here. So that's the history. It's nothing very special. Here, some remaining remarks on the intro. So what I try to tell you here is that Bayesian inference is not novel. It's also not a method that you go to if you don't like your results from the t-test and say, the data don't look back, it's so noisy. Let's do Bayesian inference, maybe it works. No, that's not how the world is. So if you have a bad signal to noise ratio in your data, then just accept that. And Bayesian inference will not give you nice results then, or something like that. So a lot of people, or sometimes I have the feeling people turn to Bayesian inference if they don't like their results. That's not what it's doing. And it won't do. So if there's no signal in your data, then also the Bayesian methods will not find any signal. What I also don't like is this whole subjective approach. So if people agree on their priors, there's nothing subjective in Bayesian inference. And of course, frequentist inference is based on models, so it's similarly subjective. Bayesian inference is also not more complex than frequentist inference. This is always what people think, that, yeah, frequentist, that's easy. T-test, that's easy. But Bayesian inference, that's hard. So kind of cognitively. No, that's not the case. T-test is horrible complex. Hypothesis testing is very complex, and better binomial inference is essentially counting the number of ones and zeros and then getting their uncertainty quantified. So it's very simple. It's also not computationally demanding per se, Bayesian inference. Of course, you can have applications that are computationally demanding, but you can, so for example, the classical models, they are not computationally demanding. So what is it then, to be a little bit positive? From my perspective, it's an application of probability theory to real-world problems. It's a very sensible, and from my perspective also, the only sensible means for reasoning under uncertainty that humans have invented. It's definitely clearer decision-oriented than frequentist inference. We will see a little bit of that here. It's the question is, why do we do all of this? Why do we want to quantify uncertainty? And in the end, it's because we want to make decisions under uncertainty in the real world, and that's what Bayesian inference is. Has clearer in mind. So you know that, and where Bayesian inference also nicely integrates utility functions, because if you look into hypothesis testing, there you have this type 1 error, type 2 error business, but you never come up with utility function that, you can, but it's not the classical way to think about it, that quantify how bad now type 1 error or type 2 error is. And of course, you can impose utility functions there, but Bayesian inference, because the things that you're uncertain about, you have a probability theory, a probability distribution about, you have quantified the uncertainty, and then you can also quantify based on how likely you think that a certain parameter has that value, can with a utility function, by multiplying it, essentially you can say, okay, and that's then how much I will win or lose. So it has a clearer decision-oriented focus than frequentist inference. And if we do things like reinforcement learning, agent-based behavioral modeling, and so on, then that's clearly to see. We will not go into that much, but a little bit. Good. What should you read? You can look at this picture. I didn't want to put a list up. So I don't know what you like. So I really like the statistical decision theory by Preiper Schleifer. Machine Learning from a Probabilistic Perspective, the Murphy book, Bayesian Reasoning and Machine Learning by David Barber. These are good books. Of course, also the good statistics books like the Castella-Berger Statistical Inference, the group book on probability and statistics, they all have Bayesian approaches. They're proper or Bayesian chapters. They're purely Bayesian books like the Lee book. Yeah. Filtering is good. This BDA3, the Gell-Mann stuff, it's okay, but it's a little bit more, it's a little bit too much on the nose, like, oh, you should do this, you should do that. Yeah. So have a look here. Ask me if you want specific or more precise reading recommendations for what you are interested in. Discuss that. Good. So that was on the history. Are there any questions about that? It's like Jesus, this one. So I'm trying to move the mouse, but it's not moving. So it's important to know that this is not something just coming up in the last year or something like that. Now we have to spend a little bit time on mathematical background, not much, but a little bit. So what we definitely need for what we will discuss then in the coming hours are some aspects of probability theory, and specifically for numerical inference and variation inference, integrals will be all over the place. And if you don't like integrals and you don't like the integral sign and it confuses you, then you will be lost fairly soon. So I have some slides on that. But before we discuss them, I wanted to actually check a little bit interactively what you know. So can somebody explain conditional probability and Bayes theorem? Or let's say Bayes theorem. Let's start with Bayes theorem. Can somebody say something about Bayes theorem? Formula. Yeah, the formula, but also the meaning. I mean, you have heard the term Bayes theory. And actually, we teach it in, we even teach it in our, so of course, Bayes theorem is just part of probability theory. So there's nothing Bayesian about Bayes theorem. So there's no Bayesian inference. But so what do you know about Bayes theorem?
To me, it's only like how probability gets updated once I get some information already from the world.
That's also what I would say. Yeah. Okay, then we have a look at that. Conditional probability. Does anyone have, if you were asked to define conditional probability, what do you say?
Like probability of occurring an event when a given set of events are defined, or factors, something like that.
Yeah, that goes into the right direction. So I think the most important thing for conditional probability is always to appreciate that you always need a joint probability of two things first. So this can be events, often conditional probability, and these things are only described in terms of events and then not in terms of random variables, but it can, of course, also be random variables, or the events that relate to random variables. So the first thing to appreciate is that you can only define a conditional probability in the setting that we use if you already have a joint probability, because we're not dealing with Markov kernels. So you have a joint probability of two things occurring, and from that you can then compute the probability that one thing occurs if the other has occurred, or occurred essentially, and that's it. It's just basically how you normalize the joint probability to be a proper probability distribution. That's everything. So the more important thing about conditional probability is actually joint probabilities. And Bayes' theorem is then basically just a formula to get a conditional probability from a joint probability in a specific way. Okay, but we will have a look at that. So these things are often discussed in terms of events and elementary outcome spaces or probability spaces. We, of course, need them in terms of random variables. So what are random variables? Who can define the notion of a random variable? Oh, who wants to define? Yeah, online? No. Yeah, so random variables, they are mappings from outcome spaces into other spaces in probability theory. So one way to look at random variables is like that, so as functions. And that's the way to look at random variables. Another way to look at random variables is as something that can take on random values, a variable that can take on random values. That's not actually, from a theoretical perspective, what makes a lot of sense, but it's also something that, as a first start, helps. Quite important are probability mass and density function. Can somebody give an example of a probability density function? You all know at least one probability density function.
It's the area under the probability curve.
Yeah, so I heard two things. So one is Gaussian that's that fits. So probably the Gaussian is one typically associates with this formula 1 over square root 2 pi sigma square exponential of minus 1/2 x minus mu square. One associates the Gaussian. Of course, one can also talk about the Gaussian distribution, but that's this formula and this bell-shaped curve that you always see. That's the density function. And what you said online, that's also that's not a density function, but that's how you get from a density function to a probability, because that's a density. When talking about densities, you should always think about physical density. So you all know the things that you learned about density in high school physics. So mass is density times volume, and that's exactly what probability density functions want to do. Probability mass functions do that more straightforwardly. We'll have a brief look at them to remind everyone of what we are talking about. But the reason why they are so important is because if you look at Bayesian inference, the action is happening essentially at the level of you can do Bayesian inference, of course, with events and in basic probability theory, but most of the time the action is happening at the level of probability density and mass functions and at the level of random variables, because you use random variables to model your parameters and your data. And hence we should have a brief look at that. And then, so we will look at that after the break, but at least there's some knowledge here. What we also, because there will be many integral signs, so we cannot just delve in there and not talk about integrals. So does anyone remember what an antiderivative is? In German, Stammfunktion. Sorry. What's an antiderivative or Stammfunktion?
Opposite of the derivative, kind of like if you take the derivative of that function, you get to the function.
Exactly, yeah. And if you look at the set of all antiderivatives, these are actually called indefinite integrals, something that I also always forget. Then we will see definite integrals. So does anyone associate anything with that, or maybe as you mentioned, as you know, that what a Stammfunktion is, what did you use it for?
Yeah, mostly for calculating like integrals
Yeah.
from, I guess a definite integral is like defined in a certain area, like from 1 to 5 or something.
Exactly, yeah. So these are the definite integrals, and we will briefly look at them. And we are only discussing here Riemann integration. So yes, let's keep it at that. And then there are improper integrals, which are the integrals which are also will show up all the time in Bayesian inference, which are integrals that encompass the whole real line, so all the real numbers, so which basically go from infinity, from minus infinity to plus infinity. These are called improper integrals, and what they are, and we will briefly look at as well, because all the integrals that we will see then later are improper integrals. I think we will also see double integrals, and I didn't bring them up here, but yeah, maybe we get to that at that point.
Is there then any difference between indefinite and improper integrals?
Yeah, indefinite integrals is just a set of antiderivatives. So that's all antiderivatives plus a constant, because, you know, if you have a constant there and you compute the derivative, it's 0. So if you have a function f and you have its antiderivative g, then g plus some constant is also an antiderivative of f. And so that's what is called indefinite integrals, and improper integrals are just integrals. And they also, okay, and I see where, yeah. So this one defines a set of functions, and improper integrals, like definite integrals, are, if they converge, are numbers. So one of them is a set of functions, and these are functions. And if everything works out, these are numbers. We will look at that. So I will bring up some slides on that after the break. But okay, so I think the integration background is quite okay. The probability background maybe a little bit shallow, but we will have a look at that. And for everything in this regard, I highly recommend also Belinda's Foundations in Mathematics and Computer Science, which is on our teaching website, which Belinda taught this year, and very well. Is she here actually? Because I'm now talking about her, and I think she's here. Yes, she's here. She did a very good job on the intro to mathematics and computer science. All the videos are online. Good. Then let's take a break if there are no questions right now, and then continue briefly after 11 with the mathematical background, and then we have everything to start with Bayesian inference properly this afternoon.
Is there maybe space for a comment on the history of Bayesian inference?
Yeah, sure.
Because how I understood it, you were talking about the contributions that people make. I was wondering if we were thinking about recent events that have been important. Would you say the replication crisis in psychology could be such an event that has triggered more attention to Bayesian statistics in general?
I don't know. So I don't know who is aware of this replication crisis, but it's, of course, this actually goes a little bit in the direction of what you just discussed. I think that's of course people try, maybe some people try to say that things are not being reproducible has something to do with frequentist inference and so on, and that people should use more Bayes, but they would have said that before, and it has been so. No, I would actually strongly disagree with that. The way inference is being done. I mean, of course, people then talk about p-hacking, parking, and so on. But that's, you can do p-hacking with Bayesian inference as well. I mean, you just create a lot of noisy data, apply your Bayesian inference approach, and something will show up, and like a p-value. So I don't think that frequentist statistics per se generates unreproducible research or something like that. I think the problem is deeper in the sense that the strong focus on positive results, which we also just heard, which you have with Bayesian, or you can have also with Bayesian inference, yeah, often, I don't know, reproducibility. I think this is a big topic, because the question about reproducibility and replicability, I think you can only hope for reproducibility in the sense of the same data, same analysis, same results. That is something we should strive for. Replicating something, yes. Under slightly different circumstances, yes, that might work. If it's a robust thing, maybe it doesn't work. The important thing is that what somebody has done is well documented and allows people to work and build their work on that work, and that it's of sufficient quality that you can actually work with what other people did before, because you have access to the data and you have access to the data analysis code in modern times, and it's also clearly written and it's informed. So that are the important things. But I don't think that Bayesian inference helps there, or frequentist inference is the reason why certain things were not reproducible also. No, I don't agree. Okay. Maybe you have a very different view there, and some people might have very different views, but from my perspective, I know that people say things like that, but I don't. So yeah. Okay, but yeah, always come up with questions, and let's discuss more if the opportunity is there. So before we then really start with the basic Bayesian models, let's briefly look into these things that we already highlighted before the break, because they are just very foundational. And I honestly, again, and clearly recommend, it depends on what you're doing, right? So if you want to just learn or hear a little bit about Bayesian inference here, that's not it's actually the wrong slide anyway. If you want to hear about Bayesian inference, there's a little bit, so you heard about things, then of course you don't need to go into no, it's the right slide, so I'm confused. Then you don't need to go into the foundations. If you just want to hear a little bit, but in the end, you're working each day with your neural network and trying to predict something from there, and you understand your neural network, that's completely fine. If you, however, actually work with frequentist statistics or with Bayesian statistics, it makes, of course, a lot of sense to understand the procedure that you're using to some depth. And then I can only recommend to look at the foundations to a certain degree, and that's just why I'm showing this here. These things that we mentioned here and discussed briefly, this is what we cover actually in the first term of psychology. Actually, Riemann integration was already covered in the pre-course, but probability theory, that's the big topic in the winter term, now starting this Thursday next week. I think the time is off. It should be 3 hours. But that's, you also find this course online, unfortunately, again, only in German, but some of the reading recommendations like Berger, de Gut, they are in English. So it depends. If you use, I think that depends on what you actually apply, what you do in your research, where you want to go into the foundations. But if you use probabilistic reasoning, or you want to, then it makes sense to go into the foundations. So I only highlight here a little bit of the things from that course. So we can't go into the details because, or we go into the details, but we can't go cover everything because then we would do that course. So this is also something that we already discussed. So this is how conditional probabilities are often introduced in terms of events. So the important thing is that we start with a probability space. Of course, you have a problem if you don't know what a probability space is, because then you don't. It's hard to understand the logic here. And of course, in this setting here, I will not now start explaining what a probability space is, because then we would do that other course. So assuming that you somehow have an idea about probability spaces from wherever, so where you have some set, you have a sigma algebra on that set, so a set of sets with certain sets in there and others not. But basically, in the discrete case, the power set, so the set of all possible subsets, and a probability measure that assigns probabilities to events, so sets, then you can define, or the conditional probability is defined as a normalization of the joint probability of two events happening. So that's one way you can see it. It's said theoretically, it's the conjunction of two sets. One thing, I mean, if all of this doesn't tell you anything, one thing you can focus on is here that the conditional probability is denoted by this this line here. So the probability of the event A given B, and that it's always conditioned here on this second thing, and the probability distribution is then about this first thing here. So you can put into this first thing here different events and all condition them on the or all possible events and condition them on B. That's then a conditional probability distribution. If we're going to random variables, using the notation of random variables, this is always the joint probability of two random variables taking on specific values, because from the mechanics of the probability theory and how probability spaces and random variables are connected, this just makes a lot of sense. Yeah, I guess that's not what you are horribly familiar with, neither probability spaces nor what random variables really are. We get a long way without going too deep into that, and also then talking about things more intuitively, specifically with Bayesian inference. But if this confuses you and you want to understand statistics, please take our course. So that's how deep I can go into that here, because otherwise we would do that course now. And we do that course starting next week. So you are, of course, all invited. So that's conditional probability. Of course, we didn't discuss anything like probability spaces or sigma algebras, and we didn't even discuss this notation here that you might also find very unfamiliar, but all of this is explained in the first term of the Bachelor of Psychology. And if you want to learn about it, join us. If you've seen all of this, then of course don't. Random variables. Random variables are functions. So if you have a probability space and another measurable space, so where you just have a set and a sigma algebra on that set, then a random variable is a mapping, which is measurable. So it's a mapping from this outcome set here to this outcome set here, and has the property that all omega in this set here, for which the values of the random variable are in a given set S of this sigma algebra here, are part of this sigma algebra here, which means that for every S in S, we can assign a measure under this inverse projection by this random variable. It's not that complicated if one builds it up step by step. Here now, of course, it appears quite complex because we didn't build it up step by step. If you want to see it built up step by step, again, our course starting next Thursday. It's also not something very particular. It's just what the whole world that deals with random variables views random variables as. So it's not something that only mathematicians think about or something. It's just what the current human knowledge about random variables is. The strange thing is then that random variables are neither random nor variables because they're mappings. The randomness comes in because we have also a way to describe that in our course, because these omega in big omega, they are assigned a probability, and the idea is that such an omega is selected according to this probability measure, and then the random variable maps this onto some other value. And of course, then one can ask, what is the probability measure for these C omegas, for the values of the random variable? And that's then what is called a distribution. So that's this image measure. So distributions of random variables always relate to this underlying probability space, which then often is also ignored, which is also a little bit confusing, but that's how modern probability theory works. Again, one can, we discussed all of that starting next Thursday. What is, however, now from what we are doing here important, and from you knowing the Gaussian and also, I guess, the Bernoulli distribution is that, or the binomial distribution, is that this formal approach about talking about what the distribution of a random variable is often quite colloquially used and also applied to probability mass functions or probability density functions. So we already had this morning when we said an example for the probability density function, the Gaussian, and then we can discuss so I would say there's the Gaussian distribution, and the Gaussian distribution has a probability density function. And then you can look at the probability density function of the Gaussian. That's this formula that you know, and the way you know the bell shape. And but then this is also often just referred to as the Gaussian. So one can make this very precise and not be confused about probability density function, probability mass function, probability distributions. That's again happening in the winter term, starting next week. These days, we essentially just need a little bit of probability mass function, probability density functions. We will bring them up, and then I will show them again, and then it's relatively clear without thinking about the real model of a random variable like highlighted here. Bayes theorem in all its glory here is essentially just a means to compute a conditional probability, and here it's actually explained quite well how. So we want to compute the conditional probability of an event AI given B. By definition, the conditional probability of AI given B is the joint probability of AI and B divided by B. So that's the definition of conditional probability. The meaning of conditional probability we also discuss in this course. It doesn't change the joint probability. It's just a normalization of the joint probability, the relative probabilities of different events given that event B is the same in the joint distribution as in the conditional distribution. This joint distribution, this joint probability, it's not a distribution, this joint probability, we can write in a different way because we can also define the probability of B given AI. That's, of course, also the joint probability, but divided by PAI. And hence we can write this joint probability here either as PAI given B times PB. So, or we can write this joint probability as PB given AI times PAI. And then we are essentially already there. This then just shows how we can go from a marginal probability of the event B back essentially to marginalizing out AI in this joint probability. Again, what is behind there is essentially a good understanding of at least discrete joint probability distributions. If that doesn't tell you anything, again, that's, I don't know when we will do that. I think it's the 4th week or so in our course. So one needs these foundations in probability theory for frequentist statistics and for Bayesian statistics. So that's why we cover them, and we will have covered them until Christmas. So if all of this doesn't tell you much, please join us. What you will have seen, and what we, because you have seen the Gaussian, are probability density functions and probability mass functions. So that's also something that we can deal a little bit easier with, because one doesn't need to. So for the last couple of slides, I showed you things that there were like 5 slides before that, and then this slide came up in the course, and then it would be fairly straightforward if one has a little bit of coffee in the head or in the body. Of course, I didn't show you the 5 slides before, so that was a bit complex or confusing then. Probability mass functions and probability density functions, which we really need, are a little bit simpler. So a probability mass function refers to a discrete random variable. So you know that there are different forms of random variables. You know that there is, for example, the Bernoulli distribution that you use to model throwing a coin. There you say, okay, heads has the probability of 0.5 and tails has the probability of 0.5. There are these 2 outcomes. They are 0 and 1, or heads or tails or whatever. It's not really whatever. If you're dealing with Bernoulli distributions, it must be 0 and 1. If you're using categorical distributions, it can be whatever. But you know that there are these things like that. And to describe them, you use, or people use, probability mass functions, where you define for each possible outcome of the random variable, in the case of a Bernoulli random variable, 0, 1. If you have a uniform distribution over, if you, I don't know whether you did experiments or something, but often in experiments, in experimental design, you choose something at random, but which usually means that you use a uniform distribution, and then often over a discrete set of events. Say you have 4 trial types, 1, 2, 3, 4, and you want each of them to have the same probability to come up at a given time, then you would usually assign a probability of 0.25, so 1/4, to each of these values. And you could then describe this, that your trial type is a random variable, takes on the values 1, 2, 3, 4, and you assign to each of them the probability of 1/4. That would be an example for a probability mass function. Bernoulli is a kind of analytical or functional example. We'll see binomial later on. So these are probability mass functions, which are just to each outcome value of your random variable, you assign a probability value, namely the probability that the random variable takes on this value. And this is, this is just, I don't know whether so I can highlight here a little bit. This is the way we write functions. So this is the label of the function P for the probability mass function. This is the domain of the function. So the values it takes its inputs is a discrete space with finitely many values. Can also be countable, so infinitely many, but not more than their natural numbers. But that's a special case. So finitely many, and it gives you out a value between 0 and 1. Including 0 and 1, and or possibly including 0 and 1, assigns to each of these values the value of this function, and that's just the probability that the random variable c takes on the value x. Because these are probabilities according to the Komarov axiom system, which we introduced, I think, in the second week of the term, they sum to 1. So if you sum over your 4 trial types, you get to 1. If you sum over heads and tails in a coin, you must get to 1. They are non-negative. Probably that's just Komarov axioms. Yeah, that's the meaning of contability. So these are probability mass functions. We will see the binomial in the conjugate inference section as a prime example of probability mass function.
So mass function is the same as density for discrete variables.
Essentially, yeah. The main difference is that in a probability mass function, you don't need to integrate to get a probability. So you define your probabilistic model in terms of, you say there's a random variable and has this probability mass function. If you then want to ask what's the probability that the random variable takes on that and that value, you just get the output directly from the probability mass function. In terms of the probability density function, which applies to continuous random variables, meaning random variables that take on real numbers. You might know that there are many real numbers, so there are uncountable many, so there are really more real numbers than there are natural numbers, which is actually the big problem of probability theory and integration and everything that happened in the late 19th and early 20th century. There you don't get probabilities from this probability density function. So this Gaussian curve doesn't show your probability, just shows your probability density at that location in the space, which are the real numbers. And if you now want to know what is the probability for this real or real valued random variable, or for this continuous random variable to take on a given value, that's, you can ask that. The answer is it's 0. So the probability that a real valued random variable takes on precisely the value 1 or 0 or 1.3 or pi or whatever is 0. But it is not a 0 for intervals. So if you, and that's then the notion and the way you have to think about in terms of density. If you want to compute mass, probability mass, you get that by density times volume. If the volume is 0, and that's the whole measure theory business of probability theory. If the volume is 0 for a real number and the volume is 0, then you don't have any probability. So the probability for the random variable to take on that value is 0. But if the volume is not 0, if you have an interval, then depending on the probability density function, you might get to non-zero probabilities, and that's described here. The probability for the random variable, this is a typo, that should be C, and to take on a value, or should be xc here, because I started to write all the random variables as xc and not x anymore, because that's confusing with respect to the second term where x is the design matrix. It's something different. The probability for this random variable to take on a value between a and b is given by the integral of the probability density function from a to b, and that's a defining feature of probability density functions. Another defining feature, and a very important defining feature, is that it's normalized. So if you compute the improper integral of a probability density function, so the integral over the entire real line, that needs to be 1. This is, again, so the probability that anything happens in terms of the real numbers is 1. That's this normalization property of probability, and it's larger than or larger or equal than 0. Probability density functions are sometimes confusing if you look at them, or people are confused if they take on values larger than 1, but this is just the confusion that it's between probability mass function and probability density functions. Probability density functions don't give you probabilities, and they can take on values larger than 1. The important thing is that what you see on the x-axis, and that this whole thing integrates to 1. And integration is area under the curve, and if you can also do that by a rectangle that you put on there. And if this is very small, and you multiply that by something larger than 1, then this of course still can get to 1. So and it will get to 1. So don't be this is otherwise, besides that, of course, if you look at probability density function, and we will look at them, you can always interpret them as probabilities, right? So you shouldn't, but visually it doesn't really make much of a difference. If you if this is something almost like a Gaussian or something, and this is a PDF, of course here you have a higher value than here, and then of course if you integrate here, you get a higher probability than here. So the density, if there's higher density and you have the identical volume, then of course you have higher probability. So this is why it doesn't hurt to think about if you see a probability density function, to think, okay, there's a higher probability for something to come out here around 0, where there's high probability density. This is correct. If you measure volume on the real line, all the time the same. If you start to measure volume differently here, and suddenly an interval of 0.1 has a volume of 10, and here there's a volume of 0.1, then of course it doesn't hold anymore, but that's not what you do. And hence you can look at probability densities and their relative values as high and low probability, but always keeping in mind that the probability is only really evaluated based on integration. And then also don't be confused if you see probability densities of 1.7. It's not the probability. So we will see examples for that, but I wanted to highlight that. I just can't give a whole introduction to probability theory here. I mean, I could, but then we wouldn't do Bayesian inference. Good. Other thing, Riemann integration, which I think worked well. So where you obviously know more, because that's also what's actually done in depth in school, I think. And then of course one forgets it because one doesn't need it anymore. But at least that's something that one learns in school. Why that much and not other things like matrix calculations or programming? I don't know. Here's that slide that I thought about earlier. So if you want to know more about integration and calculus and set theory and functions and so on, that's our pre-course where we do that, mainly discussing things that you did in school. But we also do of course more than we do here today, because I will not give you the definition of the Riemann integral, and I just will appeal to intuition. So these are just the things that we discussed earlier on, just formalized. And this is mainly about notation, because we will just see many of these integral signs. So the antiderivative, as we already discussed, is if you have a function that takes on a single argument and gives you a real value out, then a function for which the derivative here denoted by this prime, this little thing here, the derivative of that is the function itself, then this big F is called the antiderivative of F. The whole set of antiderivatives of a function f, that is all functions that have this probability plus some constant, that's called the indefinite integral of f, and that's denoted by this sign. Although I already have to warn you, in applied settings in Bayesian inference, there are no exception. We will write improper integrals the same way. So the integrals that we will see will always be improper integrals. So over the entire real line. Formally, one should always carry the minus infinity or r, but if one does that all the time, it looks just very noisy, everything. So I'm just trying to point that out here. We'll point it out again when we when we look at improper integrals. So for the Germans here, the main thing is Stammfunktion, and that you remember that. What can we use Stammfunktion for? That's what we already discussed. We can compute definite integrals. Why do we want to compute definite integrals? In probability theory, well, one thing is that we want to actually evaluate the probability for a continuous random variable. Why do we want to use continuous random variables? Because we have continuous measurements, or at least think of them as continuous. We can compute probabilities for random variables to take on values between two boundaries, A and B. And that's, of course, the intuition is there, the area under the curve. Here, there's a bigger area under the curve. It is important that it's a signed area under the curve. So the integral here, for example, of the sine function is 0, because there is a negative number and there's a positive number, and they're the same. And then you add them. So I omitted the formal definition of the Riemann integral here, which works by a limiting process in terms of Riemann sums. We will see Riemann sums in numerical inference. This is just when you put, like you also do in school, when you put rectangles here and try to approximate a continuous function by these rectangles, and then you make the rectangle smaller and smaller and smaller. We will see that for numerical integration later on. And then I looked at this definition, and it just required 3 more slides or so to make clear what this definition wants to say. So I appeal to your intuition in terms of what an integral is, so the signed area under a curve. How to compute it, I think everyone remembers from school, because that's what you did there a lot. If you have a definite integral from one boundary to another boundary, you can compute it according to the second fundamental theorem of calculus by putting into the antiderivative the other boundary, the lower boundary, subtracting them from one another, and that's then the same as that. Why that is interesting, and something that Belinda covered in the pre-course. I guess I haven't really watched the video, but I guess she did, because it was on the slides. But then I also don't remember how deep I went into that. It's actually not so. From school, I of course also remember that, but I doubt that this was ever properly explained in school why this actually works. It works, and it feels familiar, so that's good. But this is called a definite integral. What we will see most of the time when we see the integral sign here, and when we see things like that here, we actually referring to improper integrals. And these are integrals where the boundaries are not definite, so in the sense that they are not real numbers, but they are outside the real numbers, namely minus and plus infinity. How are these things defined? And this is how this works. So they are actually defined in terms of definite integrals. So here you have the definite integral, which we at least know how to evaluate, even if we have not defined what it really is. And the idea that we move either boundary, so we have a limiting process of either boundary to minus infinity or plus infinity, and then an integral. So here we just have a limit. Of course, that poses the question: what is actually a limit? That poses the question: what is actually a sequence? And that's something that is still not in the pre-course. At one point, it will be in the pre-course. But of course, intuitively, you can think, okay, A is getting smaller and smaller and smaller, close to minus infinity. And then the question is, what happens then? And this is then the whole real analysis business. But nevertheless, we can describe what we mean by this setting here. So an integral sign over the entire real line in terms of one limit plus another limit, namely these two limits. And these two limits then defined again in terms of definite integrals, and then everything builds upon each other, and we do something properly mathematical. And we have already seen an improper integral, namely of a probability density function that always needs to be 1. That's just a defining feature. Like in all definitions, we don't need to ask why that is, but we need to work with the definition. Now, again, the point that I'm trying to convey here is that we will think of improper integrals most of the time. So we will integrate out, for example, from a joint distribution one argument. So from a joint probability density function that then is, this will be over the entire real line, but we will write this all the time like this. So this R or this minus infinity and infinity will not be there. That doesn't mean we mean indefinite integrals, but we mean improper integrals, so integrals over the entire real line. And that's also, so it's, if you open any machine learning book or any modern data analysis book, you will hardly see this, or even this. You will mainly see this, and it's understood that this is an improper integral. Good. So this are just very briefly and very shallowly some mathematical foundations that I just wanted to mention. I know that I didn't cover them in enough detail to really understand what's going on, but at least I said something about integrals that will show up, and at least I said something about probability density functions and so on that will show up starting then in the first session in the afternoon on the foundations of Bayesian inference, because that was the morning session, that was all preliminary stuff, but now at 1 p.m. we start with Bayesian inference. There's no more preliminary stuff. Yeah. Any questions right now? I know it's too shallow, but it's just doesn't. So this is what has driven me nuts forever. That somehow statistics is taught, and machine learning is not a problem, but statistics is taught without probabilistic foundations. It just doesn't work. You cannot teach statistical inference without properly teaching probability theory. It's just because statistics and statistical inference and t-tests and linear regression, if you want to assign significance to or confidence intervals to your estimates, beta parameters, or whatever you call them, slope and offset parameters, this is all application of probability theory. And if you don't establish the probability theory foundations properly, there's no chance in ever understanding what probabilistic inference wants. So please join our course, read a good book, if you want. If not, go through your life and have fun.